Alright, we're on Unit 11 for the final exam review. We're going to start with numbers 6, 7, and 8. They're all dealing with the use the graph to find the limit if it exists at the particular point that you're given. So for each of these, we're told find the limit as x approaches 2, 1, and then negative 1. And we know that that means look at what's happening to the y value of the graph as the x value gets closer to positive 2 from both the left and the right side. So if I'm looking at the left side of number 6, moving in towards that value of positive 2, my graph is going down and it's actually approaching negative infinity. As I look at the right side of my graph getting closer to positive 2, my graph is going up towards positive infinity. Since the limit from the left and the limit from the right are two different values, we can say that the limit does not exist. For number 7, as x approaches positive 1 from the left-hand side, my y value is approaching positive 2. It looks like my graph is getting closer and closer to 2. And as I approach positive 2 from the right-hand side, positive 1 from the right-hand side, my graph is coming down and approaching positive 2 as well. So since the limit from the left and right approaches the same value, my limit is 2. Now it does not matter that the function doesn't actually exist at that point. It's just what it appears to be, or what it should be approaching at that point. And finally, number 8, as x approaches negative 1, so negative 1 is along this path here. So again, as I look from the left-hand side, my graph approaches, it looks like positive 3. As I approach from the right-hand side, my graph again approaches what looks like positive 3. Since the right and the left limits are the same, I can say that the limit is 3. Alright, for 14, find the limit of 5 minus 2x minus x squared as x approaches negative 2. It tells us in the directions use direct substitution. We always want to use direct substitution as long as we are able to do so without the function being undefined or having no real solutions. So when I look at this, I'm going to start by just evaluating the function at negative 2. So I do that by plugging in 5 minus 2 times negative 2 minus negative 2 squared. So I get 5 plus 4 minus 4. So my limit as x approaches negative 2 of 5 minus 2x minus x squared is 5. Alright, number 18, same as 14, evaluating the limit. Again, if I plug a negative 1 into the function, I'm going to be good. So I'm going to go ahead and use my direct substitution. 5 minus negative 1, the square root of that gives me the square root of 6. So my limit as x approaches negative 1 of the square root of 5 minus x is equal to radical 6. Right, 26, I need to evaluate the limit again, this time as t goes to 3. The problem though that I see right away is if I try to plug in a 3 or try to evaluate this function when t is 3, for the bottom I get 3 take away 3, which is 0, and I know I can't divide by 0, so I have to use some other method. And the things that we came up with in class were to multiply by the conjugate if necessary, or try factoring or something else to manipulate it to get rid of that that part of the expression that's going to make it undefined. So what I'm going to do first is I'm going to factor the top of this equation. That's a perfect square binomial, so that's going to factor to t plus 3 times t minus 3, and it's still divided by t minus 3. Now my factor of t minus 3 on the top and bottom cancels out, and I'm left with the limit as t approaches 3 of simply t plus 3. Now that I have that, that's just a linear equation that's evaluatable for all real numbers, so I can use my direct substitution now. So t plus 3 becomes 3 plus 3, so my limit is 6. Alright, 28. This time I'm going to evaluate the limit of x plus 1 over x squared minus 5x minus 6 as x approaches negative 1. Just because of what we know about the context of this problem in general, if I try to plug in a negative 1 here, negative 1 squared minus 5 times negative 1 minus 6, I'm going to get 1 plus 6 minus, 1 plus 5 minus 6. That's going to cancel out and I get a 0. So we obviously can't just do direct substitution. So I'm going to look for some other method to eliminate something. And so I'm going to try to factor the bottom. So the limit as x approaches negative 1 of x plus 1 over the bottom is going to factor to be x plus 1 times x minus 6, because negative 6 times positive 1 is negative 6, negative 6 plus 1 is negative 5, and once again now we see that those two factors cancel out. I'm left with the limit as x approaches negative 1 of 1 over x minus 6. Now I can use direct substitution, so this limit is going to be 1 over negative 1 minus 6, which is negative 1/7. Okay, number 32. Limit as x approaches 0, 1 over x plus 1 minus 1 over x. Once again, right away we see that since there's an x in the denominator and we're trying to evaluate it at 0, that's not going to work. So the first thing I'm going to do is I'm going to get a common denominator on the top. And the way we're going to do that is by multiplying the negative 1 by x plus 1 over x plus 1. So that's going to give me the limit as x approaches 0 of 1 over x plus 1 minus x plus 1 over x plus 1 all over x. Now we can combine the numerators. So we got 1. Don't forget to distribute that negative sign to both terms. We got 1 minus x minus 1 over x plus 1 over x. It's going to continue to reduce to, these are going to cancel out, so I get negative x over x plus 1 over x. If you think about this second division, we can move that up by changing it to multiplying by the reciprocal, which is 1 over x. So this thing just goes away, it turns into that, and I'm left with the limit as x approaches 0 of, since those x's now cancel out, I get negative 1 over x plus 1, and now I can evaluate it at 0. So my final answer, the limit as x approaches 0 of negative 1 over x plus 1 is going to be, when I plug in a 0, I get just a limit of negative 1. 34, once again, find the limit. I'm going to have a very similar issue if I try to plug in a 0 for v, not going to work. In this case, because I have a radical at the top, I'm going to multiply this entire expression by the conjugate, and the conjugate is going to be radical of v plus 9 plus 3 over radical of v plus 9 plus 3. When I do that, these two binomials up here, when they multiply together, it just becomes, there's a difference of squares. So I'm left with the limit as v goes to 0 of, we're just going to square the first term, square the back term. So squaring the first term gives me just v plus 9 because those cancel out, and squaring the back term gives me a negative 9, and that's all over v times the quantity square root of v plus 9 plus 3. Continue to reduce that down. The 9's cancel. These v's are going to cancel as well after those 9's cancel, and now I'm left with a 1 over radical v plus 9 plus the extra 3. Now I can plug in the 0. That's going to be 1 over radical 9 plus 3, which is 1 over 3 plus 3. So the limit as v goes to 0 of radical v plus 9 minus 3 over v is equal to 1/6. And I should point out at this point that the direction said to verify your limit on a graph. We could very easily plug any one of these functions into the graph. And for this one, as our table gets close to 0 for x, our y value should approach, in this case, 1/6. 66. Find a formula for the slope of the graph of f at the point x, f of x, the 2 points that were given. So a formula for the slope of the graph of f, that's just going to be the difference quotient. We learned in class that there's a trick to this as well, but using the difference quotient, that's going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Go ahead and plug in for x plus h and x respectively. So I've got the square root of x plus h minus the square root of x all over h. This is very similar to the one that I just finished doing, number 34. So we're going to multiply by the conjugate, square root of x plus h minus the square root of x over radical x plus h plus radical x. So we're going to get the limit as h goes to 0 of x plus, not 2, don't know where that 2 came from, x plus h minus x, or because we're just squaring the first term, squaring the last term, and then I've got h times radical x plus h plus radical x, and that's going to leave me with the limit as h approaches 0 of the x's cancel, the h's are now going to cancel. I've got 1 over radical x plus h plus radical x. Now I can evaluate it as h goes to 0. So this is going to cancel out, and I'm left with 1 over 2 radical x. That is my formula for the slope. Now I'm going to use that to answer A and B. So for A, I've got 1 over 2 times the square root of 1, which is just 1/2. So the slope at 1 is 1/2. And then I've got 1 over 2 times radical 4. That's going to be 1 over 2 times 2, which is 1/4. So the slope at 4 is 1/4. 72, find the derivative of the function. So that's going to be f prime of x. And we could use the difference quotient. It definitely works. It always works. It's a very sound and fundamental way of finding the derivative. But we also discussed in class that when you have a simple polynomial like we have here, you can cheat. We can use some magic, and we do that by taking the exponent, multiplying by the coefficient, and then reducing the exponent by 1 for each individual term. So negative x cubed becomes negative 3x squared. And then 4x to the first becomes just plus 4. And that is my derivative of 72. I'm going to go ahead and do 74 now as well. I've got g of t is equal to the square root of t minus 3. This one I am going to use the difference quotient because you have to do something called the chain rule without it, and we haven't talked about that in class yet. So let's go ahead and set up the difference quotient. It's the limit as h goes to 0 of the square root of t plus h minus 3 minus the square root of t minus 3 all over h. So I get the limit as h goes to 0. I'm going to go ahead and multiply by the conjugate of all this. So t plus h minus 3 plus t minus 3 over t plus h minus 3 plus t minus 3. So that conjugate, we're going to square the first and the last terms and get t plus h minus 3 minus t minus 3 all over h times the square root of t plus h minus 3 plus square root of t minus 3. And if I keep working this out, the limit as h goes to 0 of, let's see, a lot of stuff cancels out here. The t's are gone. Oh, I forgot to distribute. So the t's are still gone, these 3's are gone, and then these h's are going to cancel because it's now the only factor left on the top and bottom. So I have 1 over square root of t plus h minus 3 plus the square root of t minus 3. Evaluate this as h goes to 0. So 1 over the square root of t minus 3 plus the square root of t minus 3. So my derivative, it's not f, this time it's g prime of t is equal to 1 over 2 times the square root of t minus 3. Alright, 81, find the limit if it exists, and then use the graphing utilities to verify your result. So I actually am going to graph it this time just to show you what's going on. But this is the limit as x approaches negative infinity. So as far left on the graph as we can possibly go. That's what we're looking, what's the graph going to do? And it's really simple. All you have to do is look and think about what's going to happen to the numerator and the denominator. If you make these x values really large numbers, really large negative numbers, the top is going to become a really large negative number. So this is a really big negative. On the bottom, you're going to get that same number and you're going to square it. And when we square it, it becomes positive. So you have a really large positive number. And it's actually an even larger positive number. So I've got a large negative number and a large positive number, and that positive number is actually increasing faster than the top. So we have, if infinity, as the closer we, or the further we get to the left, the further apart this denominator is going to get from the numerator. So think about having like a negative 1/2, and then a negative 2. Negative 2/4, and then a negative 3/9, and then a negative 4/16, and then a negative 5/25. So the bottom keeps pulling away from the top. It keeps getting larger quicker. So what's going to eventually happen, if we're looking at a like the actual values, like a 1 over 2 is obviously 0.5. 1 over 3 is 0.3. 1 over 6 is 0.16. 1 over 20 is 0.05. So the further these two numbers get apart, the closer my value gets to 0. So even though the top is negative and the bottom is positive, because the bottom is increasing at a quicker rate than the top, it means that this whole thing, this limit, as x approaches negative infinity of 2x over x squared minus 25, since the bottom is getting bigger quicker than the top is, that means we have a limit where x is approaching 0, or where my function is approaching 0. So my limit is 0. And if I look at the graph, so I'm going to make the graph real quick, 2x over x squared minus 25, and I graph this. Look what's happening to my graph. So in between negative 5 and positive 5, there's some weird stuff that's happening. But as x keeps getting smaller and smaller and smaller, going to negative infinity, so I keep going left and left on the graph, my blue line, the actual function, is getting closer and closer to 0. So the further I go to the left, the further or that smaller that value gets. So my limit as x approaches negative infinity is 0. Alright, last problem, number 84. This time it's the limit as y approaches positive infinity for 3y to the fourth over y squared plus 1. So we're going to do the same thing we did on 81. We're going to think about what happens to both the top and the bottom as y becomes really large, this time positive numbers. So I'm going to take some really large positive number, I'm going to raise it to the fourth power, so it just got a lot bigger, and then I'm going to multiply it by 3. So the top becomes some extremely large positive number, say positive, because it's really positive, over the bottom, I'm going to square some positive number, so it's going to get big, and then we're going to add 1 to it. So that's just kind of positive. It's still a really big number, but it's not as big as the top, because the top is being raised to the fourth power, the bottom is only being raised to the second power. So if we start thinking about some numbers that we could pick, if we just pick like the number 1, just for like y to the fourth over y squared, I'm not even worried about the 3 and the 1 right now. If I just have like a 1 and a 1, obviously that's fine, but as soon as I put in a 2, I get 16 over 4. I plug in a 3, and I get 81 over 9. So I'm going from 1 to 4 to 9. If I plug in a 5, well, I guess the next number to try would be 3. I'm sorry, 4. 4 to the fourth is 256 over 16. And 256 over 16 is just 16. So these are getting bigger and bigger and bigger. The top is always going to increase at a quicker rate than the bottom, as it's more positive than the bottom is. It's a larger number. So if that's the case, my graph has to be going up and up and up and up and up. So that means that my limit as y goes to infinity of 3y to the fourth over y squared plus 1 does not exist. There is no limit because it keeps going forever. And I can verify this on a graph. If I graph this function, I have 3, I'm going to have to use x to the fourth over x squared plus 1. And when I graph this, we can see that as x gets larger and larger and larger, my graph is it just looks like a parabola. It's just going to keep going up and up and up and up and up forever and ever and ever and ever. So the limit does not exist.